right, so hello, good morning, everyone.
Good morning, sir.
Good morning. Okay, so time check, it's already 8:05, so waiting time is already over. So let me just check if you guys are already in front of your computers. Just give me thumbs up so we can start right away with our discussion. Okay, this one. What about the others? Mr. Segun and Mr. Francis, Mr. Cinder. Okay, so Miss Paklana is not here yet, maybe. And Mr. Bradley Mina is not also around, maybe. All right, anyway, so maybe they just went to bathroom. Okay, so before we start with the chapter 5 or the module 5 clampers, so anyone who has a question or clarification so far regarding with our discussion last meeting? Anything that you guys would like to ask or confirm maybe? Okay, so I guess none. All right, so I just have a favor. Okay, so may I request everybody to open the camera so that I can see your faces while I'm discussing. It would be better if I can see your reactions while I'm speaking, because it would be hard, and it's always awkward to speak to like I feel like I'm talking to the air itself, because at the same time no one is responding. So even though you're not responding, I can see your face. So anyone? La? None? None of you guys would like to open your camera? You guys are being super shy. There you go. See? That's better. Okay, so even though you're not responding, okay, so I can see your faces. So don't be shy. It's okay. So most of us here just probably just woke up. Okay, we don't have uh yeah. Some of us haven't eat our breakfast yet. So in my case, I'm just I just drink coffee in the morning, and that's it. Okay, so it's already good. Okay, so at least there are three faces that I can see while I'm discussing. All right, so let's start now with our discussion on the clampers. So let's start with the question, what is a clamper? So before we've started with clippers. So in clippers, we can change the level, okay? Like, or we can limit the level of your waveform. But in here, so whatever is your input, it will stay as it is, okay? So that is their main differences. So in here, a positive and negative peaks of the signals can be placed at desired level. So you can put it upside or downward, okay? So using the clamping circuits, as this level gets shifted, the clamper circuit is called as a level shifter. So the last topic was also called the chipping circuit or the clipper circuit, but this one is also called the level shifter. So we can say that level shifter is equal to the clamper. Okay. So clamper circuits consist of energy storage elements like capacitors. So before, we don't have capacitors in our circuits, but in the clampers, there is now an additional one, which is the capacitor. So I hope you guys have already an idea what is a capacitor is, and then how does it work. Okay. Because if no, then you're going to have a hard time. What is the functionality, or why that capacitor made our waveform like this. Okay. So in other words, clamper circuit changes this level of the signal to desired level without changing the shape of the signal. So just like what I mentioned a while ago, whatever is your input, it will stay as it is in our output. Okay. It's just that you can shift this one whenever, wherever you want it. Like could be on the upper portion, or it could be, some part of the upper and then the bottom, or it could be on the bottom portion. Okay. All right. So yes, Mr. Agustin. Oh, bakit nagsipa kayo ng camera? All right, so maybe they're going to do something. Anyway, so yeah, that's the definition of a clamper. So again, a clamper is composed or consists of a diode, resistor, and a capacitor. So before it's just a diode and a resistor, but in here we now have an additional one, which is the capacitor. Okay, and in here, in order to maintain the time period of the waveform, okay, so we have this tau. Okay, so this tau is the time that it would charge the capacitor. So tau must be greater. Half the time period discharging time of the capacitor should be slow. So this is the tau itself, or the charging time should be greater or at least equal to our discharging time. Okay, so how do we complete that one? So we will have a formula with this one. So this is just the idea. Okay, this is not the complete formula, but yeah, close enough. Okay, with this R and C. Okay, so R is the resistance of the resistor employed, and then C is the capacitance of the capacitor used. So basically, your charging time should be like instant or 5 times greater than the discharging time. Because if this one is lesser than the discharging time, then uh, that only means that capacitor is not working properly. Okay, so it's a defective capacitor. Okay, so it should be greater than or at least equal to our charging time, or I mean discharging time. Okay, so just wait a second, guys. 10 seconds. All right, so sorry for that. I just make out outside since uh medyo magulo. Anyway, so again, the time constant of charge and discharge of the capacitor determines the output of a clamper circuit. So we should have a correct relationship of between those two. Okay, so in other words, charge should be greater than the discharge. Okay, because if discharge is greater, then we won't be able to determine the correct output of our uh, waveform or our clamper circuit. So in a clamper circuit, a vertical shift or of upward or downward takes place in the output waveform with respect to the input signal. Okay, just like what I mentioned a while ago, it just shifts the level of your input. Okay, and then the load resistor and the capacitor affect the waveform. So the discharging time of the capacitor should be large enough. Okay. Anyway, so here are the types of the clamper. So we have positive clamper, we have negative clamper, and then of course we have positive and negative, but with biasing voltage. Okay, so it's quite the same with our clipper. And we could already see that, the positive clamper without bias is already a bonus. Okay, the same with negative clamper without a bias, it's already a bonus. Okay, since they are very, very straightforward, we just the use of one formula can already answer those two. Okay. Anyway, let's start with the positive clamper circuit so you guys will know what I'm talking about. So here is the only formula that you guys need to memorize when it comes to a positive clamper circuit. And this one is ideal. Okay. Well, nevertheless, if this one is ideal or non-ideal, it's the same. Okay. So in here, we have this configuration. So we have the voltage input, and then the capacitor is placed right here, and then the diode is right here, and then the load resistance is right here. And then we read the voltage output across this paths right here. Okay, or to be specific, just this load resistance. Okay. And then since this one is called positive clamper circuit, so our voltage input, which is positive and negative, will be shifted into a positive output only. So our output is clamped into a positive side only. Okay. So if you are going to put this one, so it's still the same with this waveform, it's just shifted above. Okay. So this is our 1 VM, and then this is another 1 VM. So if you're going to add those two, of course, we now have twice of the VM. So you can actually draw a line right here, which is, the zero part, okay, or the origin part, okay, before the positive and then the negative. All right. So I hope we're clear with the structure. So this is the only thing that you guys need to be familiar with. So yeah, uh, you can memorize this one if you want, but no need to memorize inside. It's open notes. But this is the thing that you guys need to be familiar with, when we're talking about, or if you're talking about positive clamper circuit. Okay, how does this one work? All right. So of course, we will start with positive or a negative half cycle. So either of those two. But let's just say that we'll start with positive half cycle first. Okay, and then we have this kind of polarity. So if we have positive, and as you guys can start here, we have positive right here, and then this one is connected to negative. So as a result, this will become a reverse bias. So if it's a reverse bias, so just leave it open. Okay, and then all of our output now, I mean all of our inputs will now go to our load resistance. So as you guys can see, whatever is our input is now also equal to our output, okay, or our VO or our RL. Okay, so yeah, usually when the input is given, the capacitor is not yet charged and diode is reverse bias. So the output is not considered at this point of time. But just to give consideration, let's say if we've started with positive half cycle, so our input is equal to our output. So it's the same for that time. But once this one became negative half cycle, so that is now the time that this capacitor will be charged. Okay, so let's proceed so that you guys will see. So in here, once we have a negative to negative and then positive to positive, so this will become a closed circuit. And then once we have a loop of current right here, okay, so as you guys can see, our current will only loop in here since, of course, it will never it will never flow on this path right here since there is a resistance. So again, going back to our uh, the rule of thumbs when it comes to current, so it will always flow to excuse me, to a path wherein uh, excuse me, to a path wherein there is a lesser resistance or there is no voltage drop. So in here, of course, there is no voltage drop or there is no resistance in here since this is just a line. Okay, so of course, it will only loop in here. And then once we have a loop on this part is VI capacitance, and then those two are this closed loop right here. This capacitor now will start charging. Okay, and in here, as I guess you can see, this will be negatively charged. So I base that one right here. So this one will negatively charge, and then this one will be positively discharged. So later on, you guys will understand what I'm talking about. Like why is that negatively charged, but once it's discharged, it's now positive. Like it's now the opposite. So that's how we charge and how it discharge its value. Okay, that's how a capacitor work in a certain circuit. So yeah, so during the negative half cycle, of course, all of our currents will only loop right here. So there is no voltage output on that one. Okay, and then at that point, let's say at this point right here, once it started to go down, I mean go up until it reaches the value of zero. So slowly, okay, step by step, slowly this will become a reverse bias again. Okay, because this one will become a positive and then negative. So we are now at the point of a positive half cycle. Okay, so once we reach that certain time, so this one now will become a forward bias. And then once this capacitor detected that there is a cut of a current or there is no flow of current on this loop anymore, this will discharge its stored power or stored electricity. Okay, so again, one good example of this capacitor is in our TV. Okay, so if let's say this is our TV, and then we have this small LED indicator right here. Like once you open that one, it will become something like say green. But once you turn off this one, this will become red, right? And then if you plug this one out, okay, if you remove the what do you call that one? The socket to the uh, outlet. Okay, so you will see that that red LED will slowly uh, like will slowly fade away. Like it's not sudden that it will go black right away or it will turn off right away. So it will slowly uh, dim. Yeah, that's proper pattern. It will slowly dim and then until it became completely black. So the reason for that is because we have a capacitor on this, of course, this television itself. So that one is a safety feature of your television. So just in case that there is a sudden loss of power, okay, it will slowly discharge, okay, all of its electricity to its component. So with that, your components will be safer. Okay. So we don't want, we don't want to have a fluctuating current on every device. Okay, so it should be slowly dissipated. So with that, our components will be safer. Okay, so I hope you guys can get the idea behind this capacitor or what is the purpose of our capacitor in our devices or appliances. Okay, so yeah, once is one detected that there is a loss of power or loss of a current, okay, so this will slowly discharge its value, okay, or its stored power. So in here, once that happen, okay, so of course this will be charged by negatively and then positively charged, right? So whatever is the value of Vi will now equal to this capacitance value. So let's say that we have a value of 3 volts right here. So this was charged negatively and then will be discharged positively. So the value of this one now is positive 3 volts. So that once we go back to the positive half cycle at this point right here. Okay. So all of our inputs now, okay, will flow now on our load resistance since this one now is an open circuit. And as you guys can see, we have positive 3 volts right here, and then we also have positive 3 volts. So just add those two, we now have 6 volts in total in our RL. Okay. And as you guys can see, we now have this formula VO is equal to VI plus VMC, or we could actually say that VO is equal to twice of VI, okay, or twice of VM, because whatever is the value of your capacitance will be coming from our voltage input. Okay, so VI is just equal with our VMC right here. So that is why from 3 volts, okay, right here, it became 6 volts. And then we have completely no current, okay, on the negative half cycle. So were you guys able to get the idea on why we have a 6 volts value right here, or why we have twice of your VI?
Yes, sir.
Okay, so this is actually the main explanation all throughout this module. So I would like to ask everybody if you guys were able to get this one, because if not, then we can still proceed to the next one, but you're going to have a hard time in understanding those preceding topics. Okay, so Mr. Awas, are you there? Are you around? So I guess he's not around. How about you, Mr. Francis?
Iniintindi ko pa po, sir.
Yes. Could you please speak louder?
Iniintindi ko pa po, sir.
Okay. What about you, Mr. Augustine?
Yes, sir.
It's clear. You were able to get the idea.
Apo. Apo, sir.
Good, good. And Mr. Sigun already responded a while ago. So very good. How about you, Miss Paklauna?
Yes, sir.
So it's clear so far.
Opo, sir.
Okay, great then. What about you, Mr. Cinder James?
Yes, sir.
Sure kayo ah. Okay. What about you, Mr. Samuel?
Sir, iniintindi ko pa, sir.
Hmm? Ako narinig. Anyway, I think he responded, but maybe
Sir,
he's not.
iniintindi ko pa, sir.
Gigising lang natin ah. Right. What about you, Mr. Jail Body?
Iniintindi pa, sir.
Okay. Mr. Bradley. Okay, so I guess he's still not around. Mr. Brian Roger.
Gets naman po, sir.
Okay. Mr. Isagani. All right. Mr. Janridge.
Sir, iniintindi pa rin.
Okay. And Mr. Arius. How do you pronounce your name?
Arius, sir. Iniintindi pa, sir.
Okay. And then last, Miss Mariel. So I guess she's not also around. Anyway, so yeah, that's the reason behind this clamper circuit. It can amplify, okay, excuse me, it can amplify or it can reduce your current, okay, depending on, of course, the components right here. So if you have a biasing voltage, depending on its polarities, it could amplify or it could reduce your amplified voltage. Okay. Anyway, so here is a summary for the positive clamper circuit. So as you guys can see right here, it says right here from the very start that the output is not considered at this point of time. So we can actually skip this one. So the question is, how do we skip this part wherein, VI is equal to VO? Because initially, of course, that will happen if that is the start of your the time you're reading of your let's say current or voltage. But after that, it is now consistently 6 volts, 6 volts, 6 volts, 6 volts all throughout, and then it will slowly dissipated into 0 again once you plug this one out. Okay, so in here all we need to do is uh you know make your diode short circuit. So this is actually like the pattern that you need to follow. Okay, so you need to make your diode a short circuit, or in other words, you have to charge your capacitor first. So when will your capacitor will be charged? So again, that is it will only be charged if we have a closed loop of current right here, or if this one is in a forward bias, okay, or it's in a short circuit mode. Okay, so at that time, this will be, or this capacitor will be able to charge a certain amount of voltage. So in here, in order for us to make this one short circuit, so we have to start in negative half cycle. So negative to negative and then positive to positive. So with that, we now have a forward bias connection. And then your capacitor now will be charged negatively, and then it will be discharged positively. Okay. So we could just say that, of course, as usual, whatever is the value of your VI will be equal to your VMC. Okay, so it will absorb everything. Okay, so if we have 100 volts right here, our capacitance now will also 100 volts. If we have 1000, then this will be 1000 also. Okay, so the same, no matter how small is your VI is. So if this one is, let's say 5 volts only, okay, or 1 volt only, then it's also equal with our VMC. So VMC stands for peak voltage of our capacitance, okay, or whatever is our peak voltage in our VI. So that is now the value of our VMC, okay. So as you guys can see right here, this one is quite weird since we've started with negative half cycle, but that's how we start with every circuit in clamper. So we have to charge the capacitance first. Okay. Then of course, after the negative up cycle, we're going now to going to have a positive half cycle after that. Then at this point, of course, diode now is open circuit, and then capacitor now will be discharged. Again, once the capacitance detected that there is no a loop of current on this point anymore, okay, so the capacitor will be discharged, and then you can use KVL to solve, the voltage output. So with that, you'll come up with VI plus VMC minus the voltage drop across this RL, okay, or this minus, like you can just call this one a minus VO. And then you can just arrange this one into something like this, which is equal to, VI plus VMC. Or you can just say that VO is equal to twice of VI, since again, VMC is just the same with our VI, or VMC is just equal with VM. So you could say VO is equal to twice of VI, or VO is twice of your VM. So either of those three, you will get the same answer. Yes, as long as your solution is correct, of course. So are we clear so far regarding with the formula?
Yes, sir.
So just give me a thumbs up just to let me know that you guys are good with this one. So basically, you only need to memorize two formula for the positive clamper. So VMC is equal to VI, that's one. And then during the positive half cycle, okay, or once the capacitor is discharged, VO is equal to VI plus VMC. Okay. Just those, or VO is equal to twice of VI, or VO is equal to twice of VM. So it now depends to you which one you want to use, since they are just the same. So let's have an example in this one so you guys can appreciate what's really happening on this circuit right here. So let me just copy this one. Okay, so it says here that calculate the V out during the positive and negative cycle, and then voltage input is equal to 5 volts. All right. So in here, we can start with, negative or positive half cycle. But of course, we will choose which will make our diode a closed circuit or a forward bias. So in this case, we have negative right here. So we should start with negative half cycle. So negative and then positive. So this is the correct one. This is the wrong one. Okay. So with that, let's start with negative half cycle. Okay, and in here, our VI is equal to 5 volts. So since this one is in a forward bias, okay, we can just simply make this one a closed circuit, since this one is ideal. So closed circuit, so we now have a closed loop of current in our, or at this point, at this VI and then capacitance. So in here, this will be negatively charged, and then it will be positively discharged. So what is the value of our VMC? Of course, that is the value of our VI, which is 5 volts. Okay, and then during the negative half cycle, VO is equal to 0, since there is no current that is flowing on this RL right here, or this resistance right here. And then VMC is equal to 5 volts. Okay, and after that, of course, it will now shift then into positive half cycle. So let's just make this one positive, and then this one is negative. And since this one is, so a while ago, this one is negative and this one is positive polarity of a diode. So positive to negative and then negative to positive. So this will make our diode a reverse bias or an open circuit. So you can just leave that one open. And as you guys can see, we now have here a, you can just use KVL. Okay, so we have VI plus VMC. Okay, so that is the output that will, or that is the voltage that will flow to our RL. Okay, so just simply follow the signage. So positive 5 volts, and then positive 5 volts is equal to 10. Okay, so as usual, it's twice of our VI, okay, or twice of our VM. Okay, so those are the things that we need to answer with a clamper. So VO and then VMC for the first half cycle, and then for the second half cycle is just the VO. So were you guys able to get this one?
Yes, sir.
Okay, so let's compare if we have the correct answer. So VO during the negative half cycle is 0, and then the VMC is equal to 5 volts. And then during the positive half cycle, we have 10 volts, 10 volts, 10 volts. So either of those three. Okay, so from 5 volts, 5 volts peak to peak, positive, negative, we now only have a positive result, which is twice of your positive half cycle. So it's now 10 volts voltage right here. Okay. So I hope we're clear with this one. So if ever that you have a question right now, so please ask them now. All right, so I guess there is no question. So time check, we now only have 1 minute and 30 seconds. So let's just have a fresh start for the part 2. So we'll stop here for now, and then we'll just continue the rest on the part 2. So goodbye for now, and see you guys later.